So your first step would be to write down all the edges, okay, in a text file. So 1, 2, 1, 3, then 2, 3, 2, 4. So we'll follow the convention, start with the lowest ID and everything that has a link to it, and so on. Then 3 has to 9, then 4 to 7, 4 to 9, 5 to 7, or 5 to 6, then 5 to 7, 6 to 8, 7 to 8, 7 to 9, then 8 to 9. So we can count the number of edges we have.
4 and 8.
4 and 9.
4 and 8.
Okay, yeah, 4 and 8. Okay, so we have 3, 5, 6, 3, 5. This is like 11, 14. So we have 14 edges. 4, 6, 8, and 14. Okay. So make sure you have all the edges, and again, don't press enter after the last line. So this should be the last line. So now save it to some file. So it is the Gurman Newman example 4, 5. So this is the original graph. So now we could determine the pairwise modularity scores for all the pairs. We should do that based on the original graph. Okay. So run the pairwise modularity program on the original graph. So it gives you all the pairwise modularity scores with any two pairs of vertices. Okay. So now we need to determine the edge betweenness values. So run the edge betweenness program and load that file. Again on the original graph. So these are the edge betweenness values. Now you can save the result to a file, like a text file or a file, so you don't have to really run it every time you need the numbers. Okay. Now, so based on the edge betweenness, these are the edge betweenness values. Okay. So what is the procedure? Once you find the edge betweenness, we remove the edges with the largest betweenness. So the largest betweenness is 9. So we remove these two edges, 2, 4, and 3, 9. So that will partition the graph into two clusters or communities. So now we need to find the pairwise modularity score, or use the pairwise modularity scores to find the modularity for each community. So 1, 2, and 3, we consider all pairs. So they add up to a modularity score of 2.25. Then 4, 5, 6, 7, 8, 9, consider all the pairs. There are some missing edges, so we have negative modularity score. So it adds up to 3.143. So the total modularity of these two communities is 5.393, the sum of 2.25 and 3.143. So we're going to assume that we can, of course, the entire graph as one community, you can add up all these pairwise modularity scores. It will be very likely less than the sum. What is the sum? 5.393. So we are assuming we would have to split this graph into at least these two communities. Now the question is, should we proceed further or not? Okay. So to decide that, what should we do? Go to this community, determine for each of this community the edge betweenness. Now this is a click. So in a click, all the edges will have betweenness of 1. So if you remove all the largest betweenness, you have to remove all the edges. So which means you will have just 1, 2, and 3 on their own. Okay, which is not going to make it a better community compared to 1, 2, 3 together. So we'll stop just with this for the side. On the other hand, if we need to decide whether to keep it as it is or break it further. So now we need to run the edge betweenness program only on the edges involving these vertices. So in the text file that we typed earlier, remove everything associated with or retain only these edges basically. So let us say a different version. Okay. So remove edge 1, 2, 1, 3, then 2, 3 is gone, 2, 4 is gone, 3, 9 is gone. So you have only these edges. Okay. So there are a total of 9 edges, so should be 9 edges here. So you can save this, and now there's another button called Open and Analyze a File. So you don't even need to close this program. Click on that button, you can open the new file. Okay. So it will again list the betweenness of those edges. Okay. So now you can plug in those numbers and remove the edge with the largest betweenness. Okay. So the betweenness is based on just this subgraph. So 4 is the largest betweenness, so you can remove 275 and 86, and that leads to partitioning like this. Okay, so now it's an indication that we should stop here because this is a click, this is also a kind of click. An edge by itself is a click, right? So if we have to remove further, you have to remove all the edges, right? So now we need to compute the moduli score of these two partitions, 5, 6 and this one. Now 5, 6 is of course a pairwise moduli score of 0.857. Now 4, 7, 8, 9 is a click, so you have edges between any two vertices. So add up all the moduli scores and it's going to come out to be 2.574. So the total moduli score is this value plus 0.857, which comes out to be 3.431. And so the sum 3.431 is greater than 3.143. So which means we need to break this further down. Okay? So the final partitioning is 1, 2, 3 as one community, 5, 6 as another community, then 4, 7, 8, 9 as another community. So the total moduli score is 2.25 plus 0.857 plus this 2.574. So that comes out to be 5.681. Okay? So that is how we should do this community detection. Okay? Secure by Newman algorithm. Any question?
When we find the modulity score, do you run the Java file or we have to use by hand?
No, just run the Java file. You don't have to do manually. Okay? Always run the pairwise modularity program on the original graph. So if you have partition and you have only a subgraph like this, you should not use this. You have to run it on the original graph. So you just run it once on the original graph and use those pairwise modularity scores throughout all the calculations. Okay? Any questions? Okay, so as I said last time, the Gilbert-Newman algorithm is very good in terms of determining very highly modular communities. Something's dim today, right? Okay, so we are going, but it's very time consuming because in the worst case we would have to run the edge betweenness algorithm for every edge removed. Okay, so it could take v to the power 5 time complexity. So we look at another metric called neighborhood overlap that has a good correlation with edge betweenness. Okay, so I updated the slide and added one or two slide. So just download this new version. Okay. All right. So the neighborhood overlap, as we'll see, will have a good correlation with edge betweenness. It's like in the node case. If you remember, the node betweenness centrality And which other metric had a good correlation? Anyone remembers that? The LCC prime BC, right? So they had a good correlation. And what did I say? So if you want to, and we did all the three correlation analysis, like the Pearson's correlation, where you can find a linear relation between the two and use the LCC prime BC values to actually kind of predict the node betweenness values, right? In addition to prediction, we also did what? Ranking, right? When you predict means just you determine the actual node betweenness values, right? That's a prediction approach. The other is ranking, which means you want to rank the vertices based on betweenness. Instead of that, you use the LCC prime BC values to rank the vertices, and the ranking is going to be almost similar to that how you get it between node betweenness, right? The other was pairwise concordance-based correlation, Kendall's correlation. So we did three correlation measures there. Like this, we are going to study the correlation between edge betweenness and neighborhood overlap with respect to ranking. So if you remember how you did this Girvan-Newman, we found the edge betweenness values, and then what did we do? We just removed the edge with the largest betweenness, right? So we kind of want to rank the edges based on the betweenness values. So if instead of finding edge betweenness and ranking, if we can find the neighborhood overlap score and then rank the edges, okay, and remove the appropriate edge, then we could achieve the same thing that we get with edge betweenness, right? So let us go over neighborhood overlap first and then study the correlation. Okay. So neighborhood overlap, as the name itself indicates, it's just like what is the fraction of your neighbors that are overlapping. So for example, so if you have an edge UV and you have, say, some neighbors like this, okay, so how many neighbors are common to both U and V? This example here.
1 and 2, 3.
1 and 2. So these are the two neighbors that are nodes that are common neighbors for both U and V, right? Isn't it? Any other common neighbors? No. So this guy is just a neighbor of U, neighbor of U, neighbor of U. Similarly, this is neighbor of U, neighbor of U, V, neighbor of V, right? Yes? Okay. So if I want to find the is the ratio of the number of common neighbors divided by the total number of neighbors, with each neighbor considered only once. So the number of common neighbors is 2 divided by that 2, the common neighbors, plus the unique neighbors. So we have 3 neighbors here, plus 3 more neighbors here. Is that clear? So this is the neighborhood overlap for the edge UV. The intersection of the neighbors, basically the common neighbors divided by the union of the neighbors. Okay? And in the union, you consider each node only once. Okay? And of course, you have to exclude U and V. So even though U is a neighbor of V and V is a neighbor of U, you should not consider them the denominator. Okay? So only those nodes that are neighbors and excluding U and V themselves. Okay? Is that clear? So that is, so the neighborhood overlap value is going to be, in this case, 2/8. So it's a fraction ranging from 0 to 1. Okay? Is that clear? Any question on how to get neighborhood overlap? Of course, we'll go through this example also. So let me see.
Question.
Yes.
Would the answer still be the same if there wasn't an edge connecting U and V?
No, we compute, yes, we could do that.
Okay.
But in this course, we will consider only or compute the neighborhood overlap for only for edges.
Okay.
Okay. Still not good. Okay. So let us see how to determine for all the edges. So one way is to write down all the neighbors for each vertex. Okay, so one has 2, 3, 5, 6, 9 as neighbors. So write down all the neighbors for each vertex. And then for every edge, find the union of the neighbors and the intersection of the neighbors. So for example, edge 1, 2. Again, each edge is counted only once, excluding those two vertices U and V. So it means when you take the union of the neighbors, exclude 1 and 2 because you're looking at edge 1, 2. So exclude 1 and 2, the union, so it's 3, 4, 5, 6, 7, 9. Okay? So that's a union of the two set of vertices. And the intersection, if you look at these two set of vertices, there's no common vertex. And if you look at the graph, 1 and 2, there's no common neighbor. So the intersection is a null set. There's no common neighbor. So the ratio is going to be 0, the intersection size, divided by the union. So the union is 6 vertices. So 0 over 6 is still 0. Okay? Now let us say 1, 3. So edge 1, 3. So 1 and 3, of course, exclude 1 and 3. So the union is going to be 2, 5, 6, 9, and 5 and 6 is already counted. So 2, 5, 6, 9 is the union, and the intersection is 5 and 6. So the common neighbors is 2 neighbors divided by union is 4. So 2 over 4, 0.5 is the neighborhood overlap for that edge 1, 3. Okay, is that clear? So this is the procedure. One more edge, so 1, 5, or let us pick something else down. So 4, 7.
1, 2, 0, why?
Huh?
There are no common neighbor?
For
Yeah,
what?
side, yeah.
So let us say 5, 6. So 5, 6 again exclude 5 and 6 and consider only the other vertices once. So 1, 3, 9 is the union, and 1 and 3 are the common neighbors. So 2 divided by 3. Because there are 2 common neighbors for 1, 5 and 6. 1, 3 is present in both, and then 1, 3, 9 is the union. So 2 divided by 2 neighbors common, 3 totally, so 2 divided by 3. 0.67 is the neighborhood overlap score. Okay, any questions so far? How to find the neighborhood overlap? Okay, so now let us try to understand how edge betweenness and neighborhood overlap would be related.
Sir, I have a question.
Yes.
Like, we are doing these things like program means like calculation.
Again, we don't have to do this manually. I have given a Java program to find the neighborhood overlap score.
Yeah, I'm asking like how to write like we are everything we are doing like manually like mathematics through like calculations. But how you can write like into program these things like we need
you
to
have
have
to know
like,
how to do programming.
no,
graph.
we need to have like a formula, right? Not like algorithm in these all steps. Like particular formula like neighborhood overlap, which has a
Yeah, so you need to know first how to process a graph. So the program I am giving you, or I have given you, reads a graph as reads that text file that you feed in with the edges, and will create nodes, edges, and so on. So it does a lot of processing. Okay, so I use Java to do this. Of course, you can use any language you want, but Java has a lot of built-in classes that you can use. Okay.
So, Dr. May, question on, let's take for example 5 and 7. So for 7,
the neighborhood overlap is 2 and 8.
No, so 5 and 7 first of all are not connected, so.
Okay, right, well, okay, we're saying for 7.
For 7 you have, it's not neighborhood overlap, it's neighbors. Neighbors are 2, 4 and 8.
Okay,
I missed 4 here, that's what you're pointing? What's your question?
okay, for what you, the formula that you went through just previously.
The formula is just intersection divided by union. So, for example, you want to find the neighborhood overlap score for 1 and 3, right? For H13.
Mm.
So all you have to do is find the neighbors for 1, find the neighbors for 3, which are given here. The neighbors for 1 is this, neighbors for 3 is this.
Okay.
And so the intersection of the, first let's find the union. So the union means just exclude 1 and 3, because you should not consider 1 and 3 when you are looking at H13. So the remaining vertices form the union. So 2, 5, 6, 9, and 5 and 6 are already counted. So the union is going to be just 2, 5, 6, 9. Is that clear?
Mm.
So that's the union of the neighbors of 1 and 3. And the intersection of the neighbors is what? 5 and 6 are present in both the sets. So that's the intersection, common neighbors. So that's how you calculate the ratio.
Okay, I know what my original question was. For 7, why is 4 not?
Yeah, that's why I said it's, I didn't list it here. Probably I should have, I have considered in the calculations, but not in the, I just missed 4 here.
Okay, okay.
So if you do 7, 8.
Okay.
So 7, 8, what is the union? 7, 8 are excluded, so 2 and 4 are the union, right?
Right.
And the intersection is just 4,
Okay.
and 4 is counted. So it's going to be 1 over 2. Okay? A good catch, so I'll go and update. Okay, so now if you look at edge betweenness and neighborhood overlap, okay? So the graph, the first graph here, not graph, just looking at the edge. So we can call this as egocentric edge network, if you remember the terminology which I introduced earlier. So an egocentric edge network means for an edge is just the edge and the neighbors and the edges connecting their neighbors. So these are the 4 neighbors of U and V, and the edges connecting the U and V to those neighbors. Okay. Now, if you look at the neighborhood overlap score for this edge UV, it's going to be what? All neighbors are common neighbors, right? No neighbor is exclusively only for U or only for V in this first graph here. The 4 neighbors and all the 4 are shared. So it's going to be what? Neighborhood overlap score is going to be 1, right? Now, if any of these green colored neighbors, if they want to communicate with any of these blue colored neighbors, or even between the 2 green colored, between the 2 blue colored neighbors, would they have to go through this edge UV for the shortest path communication? Yes or no? They can just communicate level. I should have drawn a different color. So they can just go through like this, or they can just go through like this, right? So none of the neighbors need to go through U and V for the edge UV, basically, right? For shortest path communication, isn't it? So no neighbor pair will be using this edge UV, right? So which means, what do you expect the betweenness of the edge UV to be? Huh? If none of your neighbors are using, just U and V will be using, right? So it's going to be a very small value. UV, they are connected to each other, so they will use that edge for shortest path communication. But no other pair of vertices will be using the edge UV, right? On the other hand, look at this kind of network for edge UV. If any of the green colored vertices, if they want to communicate with the other side, they have to go through this edge UV several of your neighbor pairs want to communicate with each other, they have to go through this edge UV. So now what is the neighborhood overlap of this edge UV here? There's no common neighbor, so it's going to be 0, right? On the other hand, the betweenness of this edge UV is expected to be much larger because several neighbors are going to go through this edge UV, right? So we see again of negative correlation. Larger the neighborhood overlap score, lower the betweenness. And the lower the neighborhood overlap score, larger the betweenness, edge betweenness, right? So that's the trend, okay, between the two. So we can also use something called complement of neighborhood overlap, which is like just 1 minus the neighborhood overlap score. So if edge betweenness and this NOVER have negative correlation, then the complement of neighborhood overlap and edge betweenness are going to have a positive correlation. You see that? So because neighborhood overlap is just a fraction from 0 to 1, I can do 1 minus of the neighborhood overlap score and determine something called NOVER prime. And that's going to have a positive correlation with edge betweenness. Okay? And we are going to see an example where we can actually determine or rank the edges based on these two metric values and see what is the correlation coefficient. So again, as I said, you don't have to determine the neighborhood overlap score by manually. You can use there's another program I have given you that you can use to the edge NOVER. Okay, you can use this to determine the neighborhood overlap score for all the edges. Okay, so for the same graph that we did earlier for edge betweenness, this is the neighborhood overlap score. Okay. Now these are the neighborhood overlap scores. So now we need to determine a complement of them. So let us go through this example. So first let us pick up. Remember how we did the Spearman's rank-based correlation coefficient? You have to find the tentative rank of the nodes there. So here we are going to do with edges. So we have to tentatively rank the edges based on each metric and then compute the final ranking. Okay. All right. So these are all the edges. There are 14 edges, and these are the edge betweenness values. So how we come up with a tentative ranking? If there is no tie, just that edge alone is having a particular betweenness value, so we can just assign a rank number. If there's a tie, we break the tie one way or the other. So here we just break the tie based on the first node ID. So if you have edge UV, you break the tie based on the ID of node U. Okay, the lower ID will be ranked higher. Okay. If still you have tie, break the tie based on the second node ID, which is the node V. Okay, so let us see this. So the largest betweenness is 20 for edge 1, 2. So that's rank 1, that's a tentative rank. The next largest value is 9, but there are two 9s, right? So there's one 9 and another 9. So since there are two 9s, of course, tentative rank, we have to give unique numbers. So 2, 4, because this is the order in which we actually feed in the text file. So this is actually going to break the tie. So 2, 4, 2, 7. So same U but different V. So 4 is less than 7. So we give 2, 4 a higher rank 2, followed by 2, 7 gets the rank 3. Is that clear? Okay. Then what's the next largest value after 9? You have 6. How many 6 is there? Only one 6. So 1, 9 gets the rank 4. Okay. All right. Then what's the next largest value? 5.5. So there are two 5.5. So 1, 3, 5.5 gets rank 5, and 1, 6, 5.5 gets rank 6. The next largest value is 5. there's no tie, so just this gets 7. And keep going. So if there's a tie, for example, the next largest value is 2, there's only one edge with 2, so that's 10. And 1.5, there are two edges with 1.5. So 3, 5 gets 11. Then 5, 6 gets 12. Okay? Then 1, you have two edges with 1. So you have 3, 6 gets 13 and 4, 7 gets 14. So use the same ordering of the edges that you used in the text file. Okay? So that's how we come up with the tentative rank.
So what you did?
You were there when we did Spearman's correlation, right?
Yeah.
So how did we do that? First find there we worked with edges, nodes. So now here we work with edges. So these are all the 14 edges. These are the betweenest values. So we have to just rank the edges based on the betweenest values. So we'll follow the convention in this case. Larger the betweenest, the lower the number, which means higher the rank. So 20 is the largest value, so it's the first rank. Okay, and then we have 2 9s. Keep a note of it because we need to know when we when you write the final rank.
I know how to like 1, 2 and from looking over there, yeah, we can write EBWC is between central.
Then the tentative rank is based on, you have to find the largest value.
Okay.
And that's the first rank, or rank 1. Then the next largest value is 9, but you have 2 edges with the 9.
Yeah.
So just keep that in mind because we need to come back and break the tie when we do the final ranking. But now, actually you have to break a tie here also for the tentative rank, which one gets rank 2 and which one gets rank 3.
Right.
So use that convention we followed to write the text file for the edges. How did you write the text file? Start with the lower ID for the first vertex, and then the second vertex you write in that order, 2, 3, 5, 6, 9. So you have 2, 4 and 2, 7. So 2, 4 gets rank 2, 2, 7 gets rank 3.
But somewhere you told us like something else.
Yeah, I'm going to tell that final rank we have to average out. Okay? Alright, so is tentative rank clear? The tentative rank should be unique numbers. Now, the final rank. The final rank is same as tentative rank if there is no tie. So for 20 of betweenest value, there is no tie, no other edge has 20. So final rank is same as tentative rank. Then the next value is 9, but there are 2 edges with 9. Okay? So the tentative rank is 2 and 3. So the final rank is going to be the average of the tentative rank values. So it's going to be 2 plus 3 over 2, so that is 2.5. So both the edges will get a final rank of 2.5. Okay? So that's the key thing you have to understand. The next largest value is 6. There's no other edge with value 6, so this final rank is same as tentative rank 4. Okay? The next largest value is 5.5. The 2 edges with 5.5. The tentative rank is 5 and 6, so the final rank is going to be the average of 5 and 6, which is 5.5. Is that clear? So when there's a tie, you have to, the final rank is the average of all the tentative rank values with numbers you have assigned. Is that clear? Any question on this? How to find the final rank? Okay? Now do the same thing based on the complement of neighborhood overlap. So the program is going to get you the neighborhood overlap scores. So you have to find 1 minus of those scores. So for example, for edge 1, 2, the neighborhood overlap score is 0. So NOVER prime, the complement of the neighborhood overlap is going to be 1 minus 0 is 1. Okay? So make sure you write down the neighborhood or the complement of neighborhood overlap score.
Sir, for 5.5 you did like 5.5, 5.5 only, right? Any trick? 5.5?
5.5, for which 5.5 you are talking about? The edge between us or the final rank? So the edge between us are 2 edges with 5.5.
Yeah.
And the tentative rank is 5 and 6.
Okay.
So the final rank of those 2 edges is going to be
Right.
also the average of
Average,
5 and 6, which is
Okay.
5.5, 5.5. Okay? So you have to consider like that. Another case, for example, 1.5. There are 2 edges with 1.5. Their final tentative rank is 11 and 12. So the final rank is average of 11 and 12. So 11.5, 11.5. Okay? So now, After you write down the complement of the neighborhood overlap scores, follow the same procedure for the tentative rank. So the largest value is 1 for the complement, so that is tentative rank 1. So make sure you follow the convention. So here, because we know, or our hypothesis is what? The complement of neighborhood overlap and edge between us are going to have a positive correlation, which means if one increases, the other should also increase, and so on, right? So we follow the convention of giving a lower rank number, which means like 1 and 2 and so on, for edges with larger betweenness. So similarly, we have to give a lower rank number 1, 2 and so on for edges with larger neighborhood overlap prime, complement of neighborhood overlap. Is that clear? So you have to follow the same order. You could switch. You could start with lower edge betweenness and give the edge with lower betweenness a rank number of 1 and so on. In that case, you have to follow the same convention for the other metric also. Okay? For node betweenness, I think I followed the other way. So it's up to you. Don't confuse. So
and over dash, what you did here?
NOVER prime is going to be 1 minus of NOVER.
Okay.
Because it's a complement. Complement means 1 minus.
Okay, we need to find first NOVER, then after
Then take the
minus
complement, 1 minus of that. Okay? The program is going to give you only the NOVER score. You have to find NOVER prime. So once you write the NOVER prime values, write down the tentative rank. So the larger the NOVER prime value, the lower the rank number, or it's higher rank, but we give lower rank number. So no, there's no other edge with 1 for NOVER prime, so tentative rank is 1. The next largest value is 0.75, and there's no tie here, so it's also just 2. The next largest value is 0.67, so the 2 edges, so it's 3 and 4, and then there's another one, so 5, so 3 edges has 0.67, and then the 0.5 you have 1 here, so 6, then 7, and 8. So just write down the order in which the edges are listed. So now for the final rank, there's only one edge with 1 for NOVER prime, so the final rank is same as tentative rank. But for the next value, also there's no tie, 0.75, there's only one edge is 0.75, so final rank same as tentative rank. But now the next value, 0.67, we have 1, 2, 3 edges with that value. So their tentative rank is 3, 4 and 5. So the final rank is the average of the tentative rank. So average of 3, 4 and 5 is going to be 4. So the final rank of these 3 edges is going to be 4, 4 and 4. Okay? Then for next value 0.5, you have 1, there's one more, 3, 4. You have 6, 7, 8 and 9. So 4 edges have 0.5 as their NOVER prime value. The tentative rank is 6, 7, 8, 9. So you have to take the average of 6, 7, 8, 9. So that's going to be 13, 21, 30. So it's going to be 7.5. Okay. So those 4 edges will get a final rank of 7.5. Okay. So once you determine the final rank of the edges based on those 2 metrics, what is the procedure? You have to find the difference in the rank based on the final rank. So final rank is 1 minus 1, so 0. Just take the difference, the raw difference, okay? Then 5.5 is the final rank here, minus 7.5, so it is negative 2. Then 7 minus 12, so negative 5, and so on. Okay? So that's the difference in the rank. Then square the difference in the rank. So 0 square is 0, negative 2 square is 4, negative 5 square is 25, and so on. Then what you need to do, what's the formula? You all remember the formula? Let me write down here. For Spearman's rank-based correlation coefficient, 1 minus 6 times the sum of all the different squares divided by n times n square minus 1, where n is the number of entities we are considering. So here n is the number of edges. Okay? So the sum of all the different squares is coming out to be 81.5. The 14 edges, So 14 times 14 square minus 1. Okay? So if you do the math, it will come out to be 0.82. So again, this is like a correlation coefficient, so its values could range from -1 to 1. So since it's closer to 1, it's not like 0.95 or something, but reasonably closer to 1. So we can still say they are positively correlated. So that means if you just want to pick the edge with the largest betweenness, right? Instead of that, just find the neighborhood overlap scores and the complement of the neighborhood overlap scores and remove the edge with the largest NOVER prime. And that would be more likely the edge with the largest betweenness. Not guaranteed though, because the correlation coefficient is not 1. So it's like, you know, there could be some cases where you're not removing the same edge, but more or less it's going to determine almost the same communities. Okay, so let us do this. So we are going to use the neighborhood overlap scores of the edges, actually find the complement of the neighborhood overlap scores and then determine the communities. Now, instead of kind of explicitly finding the NOVER prime values, we know that NOVER prime is positively correlated with edge betweenness. So edges with larger betweenness will have a larger NOVER prime, which means also lower, just NOVER. Right, isn't it? So that's what we saw in the example graph.
What you said, can you repeat that sentence?
Right. NOVER means neighborhood overlap. The edge here with lower betweenness, because no neighbor will go through this edge, right? Will have a what? Larger neighborhood overlap, because all the neighbors are common neighbors. That's the reason we went through all this analysis, right? So there's a negative correlation between neighborhood overlap, NOVER by itself, and edge betweenness. So what was the procedure we did with Girvan-Newman? We removed the edge with the largest betweenness, right? So instead, what we should do with the neighborhood overlap, remove the edge with the smallest NOVER score. That will automatically take care of all the negative correlation. Okay, so that's the thing we are going to use. That's the idea. So you could find the NOVER prime and remove the edge with the largest NOVER prime, but that's not needed because it's equivalent, similar, right? So find all the NOVER scores and remove the edge with the smallest NOVER score. That is equal to removing the edge with the largest betweenness, more likely, right? All right. So these are the NOVER scores of the edges. So edge with the smallest NOVER score is 1, 2. So if you remove 1, 2, it's going to partition the graph to 2 communities. So you're going to have 2, 4, 7, 8 as one community, and these 5 vertices as one other community. So you have 1, 3, 5, 6, 9 as one community. So again, compute all the pairwise modularity scores. Find the modularity score for each community. Okay. And the sum is going to be 7.34. You all know how to do this, right? Find the modularity scores. So now we need to decide whether to proceed further. So we are like this. So 1, 2, 3, 9 broken down to 2, 4, 7, 8 and 1, 3, 5, 6, 9. So we need to decide whether to continue further. Now if you look at 2, 4, 7, 8, or you can work with one of any partition. So if you run through the edge betweenness program on this graph, just with these involving these 5 vertices and the edges connecting them, these are the neighborhood overlap scores. So you see they might change depending on whether you're looking at the whole graph or just the subgraph. Okay. So now again, what should we do? Remove the edge with the smallest NOVER score. So the smallest NOVER score is 0.33. So there are 2 edges with 0.33. So you have to remove both of them.
So we need to find those scores, right?
Yes.
With that formula.
With the program.
Yeah.
Okay. So remove the two edges, so 9 gets isolated. Okay, so 9 is on its own community, 1, 3, 5, 6 on their own community. So the modularity for 1, 3, 5, 6 is going to be 3.02, and the modularity for 9 on its own is 0. So 3.02 plus 9 is going to be less than 3.95, which means should we partition 1, 3, 5, 6, 9 or keep it as it is?
Keep it.
Keep it as it is, right? Only if you can improve by partitioning the modularity score, we can partition. Otherwise, you just keep this community as it is. Now, for 2, 4, 7, 8, if you go ahead and determine the NOVER scores, it will come out to be like this 0.5, and just this edge will have 1. Okay? So the smallest neighbor overlap score is 0.5, so which means you have to remove all the edges other than that diagonal edge. So it will come out like this. So which means 4 and 7 will be in one community, 2 and 8 on their own. So again, this is just a pair, right? So their modularity score is going to be less than 1. It's going to be positive, but it's going to be less than 1. And these, what is the modularity for these two nodes on their own? It will be 0. So the sum of all the modularity scores is going to be what? So it's going to be 2, 8 on their own, and 4, 7 less than 1. So the sum is going to be still less than 1. And that's going to be less than like 3.3 or something we get for 2, 4, 7, 8. So it doesn't make sense to partition 2, 4, 7, 8 further. So these are the two communities finally. Now if you run this through the edge between this program, you also ended up with the same two communities. Okay? So again, not guaranteed for all graphs, but kind of likely, okay, because of this strong correlation between them. Okay? Any question?
Doc, how are you getting 9 and 0?
The 9 is on its own community if you on your partition.
Right.
So the modularity score for any vertex on its own community is 0. Okay? Similarly, 2 and 8 also have 0. Okay? So it has several examples which you can go and practice. Okay. So let us now look at some more on neighborhood overlap. So we saw two algorithms already for Girvan-Newman version for community detection, right? One using edge betweenness, the other using neighborhood overlap. All right. So the Girvan-Newman version on edge betweenness is going to take a lot of time, so it's time computation intensive. Whereas the Girvan-Newman based on neighborhood overlap will not take much time because computing neighborhood overlap scores is not very time consuming. So this is a computationally light version, okay, which means less time consuming version of Girvan-Newman. Okay. Now another kind of community detection algorithm or approach based on neighborhood overlap, okay, is using this idea of weak ties and strong ties. Okay. Now in social networks like in Facebook and all the social networks, you could observe that if say you have if A and B have a lot of common neighbors, okay, of course A and B have an edge, and they also have a lot of common neighbors, and A and C also have common neighbors, a lot of common neighbors, right? Then more likely B and C have an edge between them.
Can you explain again?
Okay, consider Facebook. You have a Facebook account?
Uh-huh.
Okay. So you have three users, A, B, C. A and B have an edge, okay, which means A and B know each other, and they also have several common neighbors. Okay, similarly, A and C also know each other, and they have several common neighbors. Then more likely, B and C also have an edge between them. Is that clear? So, which means we can, if you brand, I'll tell what is a strong tie, but let us say if two edges, AB and AC, have a strong tie. So A has essentially a strong tie with B and strong tie with C.
BC.
Then B and C should at least have a weak tie. So what is this strong tie and weak tie? Okay?
Direct connection, indirect connection.
No. So tie means an edge. Okay? So we classify, of course there are different ways you can classify a strong tie and weak tie, okay, for an edge. But the way we are going to do is, we will fix a threshold NOVER score. And now that we know we can calculate the NOVER score for any edge, we'll fix a threshold, means like some cutoff. So if the NOVER score for an edge is less than or equal to the threshold, okay, less than or equal to the threshold, then we can say that edge is a weak tie. If the neighborhood overlap score is above that threshold, which means larger neighborhood overlap score above the threshold, then that edge is a strong tie. Is that clear? So for example, if the neighborhood overlap score, if you just look at as it is, what's the neighborhood overlap score for this edge? It's going to be, what are the common neighbors? The two common neighbors, right? And you have the two common neighbors plus these three neighbors. So you have 2/5. So 0.4 is the neighborhood overlap score for this edge AB. Similarly, this AC also has 0.4. Let me add one more neighbor. So that's going to make it like what? Two common neighbors divided by the two common neighbors plus 3 here and 1 here. So it's going to be 2/6. So assuming everyone knows by now to calculate the neighborhood overlap score, right? So this is 0.33. So the neighborhood overlap scores for AB and AC are 0.4 and 0.33. So now let us say I calculate the neighborhood overlap scores for all edges like this, and I fix my threshold neighborhood overlap score as say 0.25. So
sir, one moment. The last neighborhood, can you please tell me again?
okay. So how do you calculate the neighborhood overlap? Take the intersection of the two neighbors. So for AC, these are the two common neighbors. So those two, the numerator plus the same two, because in the denominator take the union, right? So that 2. Plus C has that one neighbor.
Yeah.
Then A has these 3 neighbors which are not common neighbors. So that's 3. Okay. So if the threshold neighborhood overlap score I fix is 0.25, then both these edges get classified as strong tie because their neighborhood overlap score is above 0.25. Okay. So this will be a strong tie, this is also a strong tie. So which means if A has a strong tie with B as well as a strong tie with C, A has a strong tie with B and a strong tie with C, then there is a property or a kind of expectation that to be satisfied in social networks at least, it's called the strong triadic closure property. What strong triadic closure property means is simply this. If a node has a strong tie with two vertices B and C, then you expect B and C to have an edge between them that is at least like classified as a weak tie. Okay? Is that clear? So you expect B and C to have an edge that is classified at least as a weak tie. So that is called the strong triadic closure property. Okay? So it's clear so far what is strong triadic closure property and how to classify a strong tie and weak tie. So if you fix your neighbor threshold score to be 0.35, then this edge AB gets classified as a strong tie. What about this edge AC? It will get classified as a weak tie because 0.33 is less than 0.35. Even if the threshold score is 0.33, this edge will be classified still as a weak tie. So the definition for weak tie is the neighborhood overlap score is less than or equal to the threshold. So if the score for the edge is even equal to the threshold, it is still classified as a weak tie. So if A has like this, a strong tie with one neighbor and a weak tie with another neighbor, you don't expect B and C to have an edge. So strong triadic closure property is applied if both your neighbors have strong tie. So if both your neighbors, or you have a strong tie with both your neighbors or two of your neighbors, then you expect the two neighbors to have an edge between them. It's like this, you know several people, A and B have a lot of people common to them. A and C also have a lot of people common to them, known to each other. Then you expect B and C to also know each other. Right? So that's common in social networks. Isn't it? So that is the essence behind this strong triadic closure property. Okay? So now how can we make use of this? So that's what we're going to see. Probably may not have time to complete, but let us get started. So in the Girvan-Newman algorithm, we went through a sequence of iterations, right? We found the neighborhood overlap scores and removed the edge with the smallest neighborhood overlap score, partitioned the graph into communities, and then took each community and found their neighborhood overlap scores and then partitioned further and so on, right? So we went through several iterations in the Girvan-Newman approach, either with edge betweeners or with neighborhood overlap. The idea here is we don't want to go through several iterations. We just want to partition the graph into communities once, and that's it. Whatever we get as partition, we want to keep them as communities. So the idea is, again, if you look at a weak tie, how do we classify an edge as a weak tie? If the neighborhood overlap score is less than or equal to a threshold, which means edges with lower neighborhood overlap scores are more likely to be classified as a weak tie. Of course, it depends on what threshold value you fix. But if an edge has a lower neighborhood overlap score, it's more likely classified as a weak tie, right? So what do an edge with a lower neighborhood overlap score indicate? Like in this graph, for example. This graph, the edge with the lowest neighborhood overlap score is 1, 2. 0.0, right? And we removed this edge, it actually broke the graph into two communities, right? So edge with a weak tie kind of acts like a bridge between two communities, right? The edges classified as a strong tie are kind of well within the communities. Like these edges will be classified as strong tie, okay, because they have several common neighbors. Whereas edges that are classified as a weak tie acts like a bridge. Okay, so if you remove the edge that will act like a weak tie, then you are more likely to classify or partition the graph into communities, right? So that's the idea here. So just classify the edges as either strong tie or weak tie, and then remove all the weak ties. Whatever be the number of edges that are classified as weak ties. Then whatever is the resulting partitioning, that's the, those are your communities. So let me reduce it. So, like this. For this graph, determine the neighborhood overlap scores, and for now, let us say the threshold score is 0.4. Later, we'll come back and see how to fix the threshold NOVER score, how to find appropriate threshold NOVER score. For now, let us assume the threshold NOVER score is 0.4. So if that's the threshold NOVER score, we can classify the edges as strong tie or weak tie, right? So any edge with the threshold with the NOVER score less than or equal to 0.4 will be classified as a weak tie. Anything greater than 0.4 will be classified as a strong tie, right? So accordingly, we can classify these edges as strong tie or weak tie. So now we need to remove all those weak ties. So what are the weak ties? Anything less than or equal to 0.4, which means this edge is gone, this edge is also gone, this edge is gone, then this edge is gone too, this is gone, this is gone, this is gone. So all those edges will go away and this will be the resulting partitioning. Okay?
So means that threshold value we have to assume.
That's what I said. As for now, assume, but later you're going to see how to find an appropriate value for threshold score. Okay? We cannot just come up with an arbitrary value. We have to find an appropriate value. We'll see the procedure for it soon. Okay? So we just removed all the weak ties and we'll take this as the communities of this graph. So of course this is not going to be as good as the communities determined using the Kirwan-Newman approach. But what is the trade-off? We could do this with less time, right? We don't need to go through several iterations. We are still capturing the essence of what? The weak ties acting like a bridge between two communities, right? So we're removing the weak ties, so which means we are more likely to determine the communities that exist, that were connected by the weak ties. Is that clear? So again, remember, weak ties act like a bridge between two communities. So this approach also identifies such weak ties that are acting like a bridge. So we're just removing them. But the appropriate value for a threshold NOVER score will decide how good is the partition. It's still like a greedy approach. So if you fix the threshold NOVER score as what? 0, right? What will happen? If the threshold NOVER score is 0, what will be the status of all the edges? Would all the edges be strong ties or all edges be weak ties?
Weak.
What you say?
If the threshold NOVER score is 0, the threshold value is 0, what will be the status of the edges? Will all be classified as strong
You
ties?
saying the way of
No, I'm
method
sorry.
and all
It's
that
wrong.
we can
It'd be
say.
strong.
All will be strong, right? Because everything will have a value greater than 0. And this
Right.
graph, of course, this edge has 0. So this will be still classified as a weak tie according to our definition, less than or equal. By removing this will not partition the graph, right? If just this edge gets removed, would it partition the graph? No. So you will conclude what? All the vertices are in one community, right? That's our conclusion. On the other hand, if my threshold NOVER score is 1.0, what will happen? All the edges will be classified as weak ties.
Weak.
So if you now follow the approach of removing all the weak ties, what will happen? Each vertex will be on its own community. So that is also not a good partition, right? We don't want to consider the whole graph as one community. That will happen if the threshold NOVER score is 0. But we also don't want to consider each vertex to be on its own community. That will happen if the threshold NOVER score is 1.0. So we should not go to the two extremes. So the kind of an optimal value for the neighborhood overlap score is somewhere in between. So that's why we call it a threshold score. So we now we don't have time. So next class we'll come back and see a procedure of finding an appropriate value for the threshold NOVER score.